All right, everyone. Thanks a lot for joining. Want to say thanks on behalf of the whole Phase3D team. And just a housekeeping note, if you have any questions, please feel free to use the Q&A button at the top of the screen. And really excited to introduce Fringe Inspection and let you guys know what we're doing at Phase3D. So we've developed this product because we've been witnessing a really exciting time in the additive industry. Um, it's really incredible, actually. Companies are using additive to scale at unprecedented speeds and using the technology for not only prototyping, but for production level parts. And as they scale, a lot of our customers are encountering challenges with reliability and repeatability using metal additive or highly industrial polymer additive. And they've told us it's very challenging and expensive to certify and qualify part quality. And that's where Phase3D comes in. We've developed a system that inspects your part during the printing process and records part quality data several times per layer, down to the nearest 1/100th of a millimeter. So customers can certify part quality. And as you're doing this, you're also able to kick defective parts out at the earliest stage possible. So not only are you developing quality data that describes high quality parts, but you're also able to get notifications when a part is showing signs of low quality or defects, when you may want to cancel your part or not send that part for post inspection or highly technical post processing. And to describe more about our product Fringe Inspection, I'd like to pass it to Andrew Holliday, who's going to describe more. Thanks a lot.
Thanks, Niall. Yeah, I'm Andrew Holliday. I'm the Applications Engineering Manager over here at Phase3D. I'm excited to be talking to you about our office and how we can aid in your additive manufacturing process. So as Niall mentioned, process variation and quality assurance are the major problems facing the additive manufacturing industry today. Traditionally, any sort of defects within the part would be found during post-inspection. Now, this can lead to months of lost lead or cost. In order for the additive industry to really take steps towards a production-ready tool, we need to, as an entire industry, move towards data-driven approaches to certification, inspection, and defect mitigation. Now, this is where Fringe Inspection really steps in. What we're doing is we are actively detecting anomalies as well as measuring the build in real time, allowing you to make corrective actions and decisions regarding your builds earlier within the process, like during the build. Now, this saves you valuable time, money, and resources. So how are we actually doing this, and what is our technology based off of? Well, Fringe Inspection is based off of a technology called fringe projection. And basically what we're doing is we're projecting fringes, which are stripes that are sinusoidal in nature, directly onto the build surface. We can then capture these fringes with a camera and look at the distortion of them. Then we can attribute each individual pixel to a height or a depth value. So in order to use fringe inspection, really you're looking at two key pieces of hardware. One is a camera and one is a projector. Now you need an angle between the two. You need time to make the measure. Our system is compatible with any powder bed based machine, and we also use existing ports within the machine. So here's an example of our data versus what you might traditionally get. On the left-hand side, we have a visual image. Now, this is something that could be an output from a machine or from a monitoring tool. The problem is images are incredibly subjective and they're light dependent. This can make it incredibly difficult to really understand the severity of the issues that are present. These lighting conditions and the resulting shadows can obfuscate or hide what is truly going on. Now, on the right-hand side, we have our output, which is a height map. And what's important here is we can not only identify anomalies, but we can discretely measure them. So we can see here in this height map near the bottom, there's a recoder hop where the recoder actually made impact with the part, resulting in the recoder lifting, then dropping down into the powder surface. Not only are we able to actually see that this anomaly exists, but we're actually able to discretely measure exactly how far down into the powder bed the recoder went. Therefore, we're able to understand the severity of these anomalies present in your build in real time. In that way, Fringe Inspection is actually a quality tool. We're not reliant on AI or machine learning. Instead, we are a unit-based and repeatable inspection technique that can be used during your printing process. So when do we actually take these measurements? Well, with Fringe Inspection, we actually take 3 individual measurements per layer. Now, the first one is taken as soon as a new recoat has been laid down. The second is taken after the laser is stopped so that we can create a height map for the actual melted layer. And the third measurement we take is as soon as that build platform is lowered down, awaiting a fresh recoat. Because we take that third measurement, what we're actually able to do is generate a height map showing you your true layer thickness across that entire build area. Now, each one of these measurements takes about 1 second at time, and we actually take them during existing dwell times in the machine. So we add no existing or additional build time. Now, here's some examples of the anomalies that we were able to detect and therefore measure with Fringe Inspection. On the left-hand side, you'll see some powder anomalies, things like recoater streaks, short feeds, recoater hops, even excess powder dropping, and out-of-plane distortion from swelling parts. On the right-hand side, we'll see some melted anomalies, things like spatter particles, powdery distribution, and even a hatch pattern of the parts. So how can early anomaly detection actually help you within your AM workflow? Well, here's a good example. Layer 1151 of this build, where was an actual build failure. Using Fringe Inspection, we were actually able to detect an anomaly as early as layer 1089 and track its growth. Now, using Fringe Inspection, you too can actually detect these anomalies quicker, giving you the ability to make either corrective actions or critical decisions on the build health and cancel these builds earlier within your process, saving you time and saving resources. Another way in which we've been able to prove the efficacy of Fringe Inspection is by running builds that include anomaly generators. This way, we're able to actually correlate these inbuilt defects directly, or inbuilt anomalies, directly to defects in the final parts. Now, what we do is we print these builds alongside these anomaly generators, and during the actual build, we take our data and generate height maps, as well as automatically detect and categorize these anomalies. Afterwards, we're able to correlate these anomalies directly to porosity found in the CT scans of the parts. In this way, our customers are actually able to generate anomaly thresholds. That way, when running future builds or running production, as soon as that threshold is met, they know that that's a critical anomaly that will result in final part porosity, so they can go ahead and cancel the build. Once again, saving them build time, post-processing time, post-inspection time, as well as labor time. Here's a couple examples of how this methodology has been used in the real world. The US Air Force has shown that 100% of anomalies detected using Fringe Inspection, there were over 47 microns in depression correlate to CT detected pores, while at NASA, 100% of anomalies, there were 42 microns or greater depressions into the powder bed correlated to CT detected pores. Using these studies, both of these customers were able to generate anomaly thresholds, allowing them to fail prints early within the process and save themselves valuable cost. Here's another example of the usefulness and the power of Fringe Inspection. Over on the left-hand side, you'll see a visual image. Once again, this is a typical output from the machine itself, or it can be from a monitoring tool. Problem is, in the middle section here, we see the Phase3D height map, and we can clearly see a streak going through this part. Now, this is an anomaly that would have been completely lost if we were reliant on purely visual-based solutions. And over on the far right-hand side, we can actually see a line of porosity present in the CT data that corresponds directly to this streak that would have been completely lost without using Fringe Inspection. Now, within the Fringe Inspection ecosystem, we do have 2 individual software offerings. The first is Fringe Operator. Now, Fringe Operators are an on-premises tool that allows you to visualize and analyze the height map data coming off of your machine. Now, this can be done in real time, or it can be done after the fact using saved data. Fringe Qualification, on the other hand, is our fleet management tool to allow production managers to look at an array of machines and view the build health for an entire production facility. Fringe qualification also uses anonymized metadata, protecting your valuable IP. Now, with that, I'm going to launch directly into a couple demonstrations and show you what our software actually looks like for a user. So right now, you're looking at Fringe Operator. This is kind of a standard page to be able to see when using the system. Now, it's really broken down into 3 individual panels here. You can see on the far left-hand side, we have a 3D visualizer. In the middle, we can look at our 2D height map data. And on the far right-hand side, we can view an actual health chart for this build, as well as an anomalies list. And I'll walk you through the usefulness of each one of these features. Now, all of this data that you see here can be viewed and loaded in real time as the machine is actually printing, or you can do your analysis after the fact by using saved data, much like I'm doing right now. Now, each one of these panels can be turned on or off depending on what kind of user experience you want and how you prefer to view this data. In the 3D visualizer, we can, of course, move it around, zoom in and out, and actually look at the details of what's going on your build in real time. We also have a number of different filters where we can say turn on or off the part display or turn on or off the anomaly display. We can also choose to view only anomalies over a certain threshold. In this case, I've chosen to view anomalies in the 3D visualizer greater than 35 microns. These anomalies are also color-coded. Yellow for streaks, blue for hops, red for general anomalies, and our part is gray there in the middle. In the center section here, we have the actual 2D visualizer for the height map data. We can see on the bottom right-hand corner that I can choose what channel I wish to view. Because we do take those 3 individual measurements per build, I can scroll through these and view those measurements individually. Right now, we're looking at the powder layer. However, if I did want to look at, say, the melted layer, I can choose directly go to that channel. Because we also have a camera as part of the system, we do take visual images. You are able to fully view them within Fringe Operator. So if I go back to my powder layer, I want to show you a couple key features and a couple useful features here within the system. Now I can see that I actually had a recoder hop from impact with the part directly seen here in the middle of this height map. If I zoom in, what I'm actually able to do is really use my cursor to hover over any individual portion of this height map. And in the top right-hand corner, I can see the actual measurement value that corresponds to where my cursor is located. In this case, I'm looking at a depression into the powder bed that's about 100 microns deep. Another interesting fact about this height map is that impact of the recoder caused excess powder to drop off of the recoder assembly into the powder bed, resulting in these heightened regions seen down below. Now, once again, I can hover over these regions with my cursor, and they're about a 400 micron bump in the powder bed. Now, if we look at something like the visual image, the severity of this powder dropping, as well as the recoder hop, would be completely lost and not understood. We could see that it happened, but we would not know the severity of it. We would not know exactly the measurement of it, and we wouldn't be able to actually build thresholds around it. Now, over here on the far right-hand side, we have our quality chart. And this can give you an incredible amount of power when you're trying to actually look at build data as a whole. We can see these spikes, which correspond directly to high anomalous regions within the actual build. In this way, if you want to have a quick screenshot of the build health, you can use this quality chart instead of, say, watching a video or flipping through individual images. I'm also able to select directly from this quality chart in individual layers if I want to quickly jump towards those high anomaly regions. We also build out this full anomaly list that can be viewed on this far right-hand side, where we can build things like those anomaly thresholds. In this case, my filters are set to having the general anomalies only appearing greater than 19 microns, as well as for streaks and for hops. Again, these are user controlled if we do in fact need to change them, or if you create anomaly thresholds for yourself. We also have the ability to tag these individual anomalies as critical or not. Now with that, I want to swap over to Fringe qualification and show you some of the abilities that we have within that software package. This is Fringe qualification. And once again, this is really a facility dashboard. Now, the main user of something like the Fringe qualification tool would really be facility manager who wants to look at the overall build health of their fleet of machines. And that can be an internal production facility, or they could be remotely monitoring, say, one of their suppliers to ensure that they are meeting their quality standards. We can see three key pieces of information here directly front and center. We can look at overall success rates for the entire fleet of machines, anomalous layer percentage, as well as overall waste based off the amount of failed prints. Now, if I wanted to view this information in a bit more detail, what I do have the ability to do is break it down by individual machine or even individual material. So let's say we want to look at machine success. Well, I can look at one particular printer, and I'll select Betty, for example. Now, if we look at our actual machine success chart for this printer, we can see that May and July were some pretty tough months for Betty, resulting in 10 failed builds in May and a total of 7 failed builds in July. Well, this could be explained by maybe something like operator error. And once that operator was trained correctly in the procedures of setting up the machine, we can see in August, September, and October, our success rate started to climb back up again. Now, if I wanted to view this information in even more detail, I do have the ability to look at these three key metrics in terms of individual builds. So let's say you're running a few key production builds, and you want to see your success rate for one of your production parts throughout the entire year. You could, in fact, do so if you wanted to. Now, what I also have the ability to do with Fringe qualification is to view a dashboard of all the live builds currently happening on my production facility or maybe at my suppliers. And once again, I can view a health chart for those prints that are currently operating, much like the one you saw previously in Fringe Operator. This way, I can remotely monitor the status and the health of these builds and know exactly when high anomaly areas occurred, so I can know to maybe notify a technician or to fail a print immediately, or that we have a quality concern on the shop floor. If I wanted to view this information in more detail and really dig into it, I can also open Fringe Operator directly from Fringe Qualification. Similarly, if I wanted to compare jobs within Fringe Qualification, I do have the ability to do so. So if I wanted to track key metrics, maybe such as cost or the amount of anomalous layers from one of my production builds over time, and compare it to maybe across different machines or for different types of builds, I do have the ability to do so all within this dashboard. Now, once again, as previously mentioned, Fringe Qualification does use completely anonymized metadata. So if you are in a controlled environment or printing parts with a lot of valuable IP, this can be used remotely to monitor your shop floor without risking any leaks. Thank you very much. And with that, we'd like to open it up to questions if you have any.
Thank you so much, Andrew. My name is Noah Mosto, Business Development Manager here at Phase3D. I'm going to help support the Q&A process here. Please use the top button to ask any questions. We have muted you all to keep the process running well. Nothing on you, just simply so that we can stay organized here. So use the Q&A. We don't have any yet. However, I can get started here. Andrew, I want you to describe a bit about the installation procedure. So as a customer is purchasing Fringe Inspection, what does this look like to have our team come on site and get them using the system?
Yeah, of course. So our team does come on site and install the system. Now, this total installation time is about 24 hours of calendar time. So typically what we would do is come in probably around the afternoon for the first day and actually set up the equipment. Now, because we use existing ports on the machine, we're not really creating any modifications or drilling in at all. So we use existing ports to mount our system and then use that day to really calibrate the system and ensure that we're in spec. Afterwards, we'll use the overnight area to pump down the machine and prepare it for a quick test build so that we can verify that our timing is correct and that we're ready to leave the next day with you having a correctly operational and machine that is actively giving you data. So it's about 24 hours total installation time. And once again, we're a non-invasive solution that's compatible with any powder bed-based system, and we really use existing ports on the machine to do so. No, it seems that you have muted yourself.
That sounds correct. So we have another question here around resolution. Can you speak a little bit about how the resolution varies for machine to machine and if it can be adjusted?
Yeah, so for something like a typical offering, like an EOS M290, for example, we're working at about 100 micron resolution in the X and Y, about 10 microns in the Z direction. Now, based on your application, if you do need higher resolution, that is, of course, an option that you can work directly with us. We've gone down as far as spec out 60 micron resolution, the X and Y. So it is really dependent on exactly what you're looking for and what sort of parts you're printing, as well as what sort of anomalies or geometry that you do need to detect. With larger format systems, there's a variety of different ways to actually achieve this resolution, whether that be higher resolution cameras or maybe multi-camera, multi-projector systems. But our solution is quite flexible, and we can work directly with any of our customers to make sure that their resolution needs are being met.
Beautiful. Thank you, Andrew. So we have a question here from Scott asking back to the installation procedure. So
Mhm.
he says, each machine would be out of operation for about 24 hours during installation.
Yeah, about 24 hours calendar time.
Beautiful. And then Scott, just for your kind of input here, really after that, you will be starting to gather data and running. So if you want to start
Yeah.
a build in the afternoon, you can turn and burn and start to gather data as soon as possible.
Mhm.
We also have a question here from Brad, and he asks, what are the key differentiators between Phase 3D's monitoring and quality software versus other competitors on the market?
Yeah, of course. And I think this is actually a great slide to show when we talk about the key differentiators here. Is really the key difference here is yes, we do actively monitor the build, and that is something that we do, and we generate all this data in real time. The key difference here is we're really an inspection tool. And Fringe Inspection and actually Fringe Projection is an inspection and a measurement tool at its core. So the real difference that we're doing here is we are actually measuring these anomalies so that you can make informed and data-driven decisions about the future of your builds and about your production moving forward. Instead of just making subjective decisions about defects or anomalies that are captured in images, we're able to discreetly measure them, giving you data-driven decisions and insights into your builds in real time. So I think that's one of our key differentiators here is we're not relying on black box, we're not relying on AI or machine learning. This is a true measurement technique that has been adopted to be used in real time during your additive manufacturing process.
Beautiful. Another question here from Scott asking around data storage. So, what are the data storage requirements for the system?
Yeah, so we do provide a computer as well as hard drives for that. We know, do you know off the top of your head what the average size of a layer is, for example?
Yeah, so I can kind of answer to this. So, we typically look at about data storage size is 50 gigabytes per 1,000 layers, and that's saving all of the height maps and and metadata within it. Now, for data storage, it's very adjustable depending on the customer. So, for example, we work in highly regulated aerospace facilities where everything needs to be air gapped. That is one side of the spectrum. The other is where we are fully integrated into a C or D drive where you can access the data wherever within the facility or any way you are accessing the other forms of data. It's very configurable depending on your facility and what your really IT department needs. So we can do anywhere in between as well. Everything is processed locally, as Andrew mentioned. So we are not needing access into the internet for this data to be processed and analyzed. Thanks, Scott. All right. On the question around competitors, there's a large push right now on artificial intelligence. And can you all talk about how Phase 3D is looking at AI today and really where you see it in the future?
Yeah, I can take that question, Noah. Yeah, it's really pertinent concerning competitors. A lot of solutions today, they use AI and coupled with subjective measurement information like maybe visual images or thermal camera images. And what we've really found and what has resonated with our customers is that using a objective inspection technology, it really helps us get a lot farther without the need for a black box AI. So while others will use an image and an AI network to pick out something that doesn't look right, we're actually recording real units and we're able to threshold our height maps um, per layer in order to find the anomalies, characterize them, classify them. We have known uncertainty and accuracy, which is impossible to collect with an AI that's looking for anomalies. But AI is a very powerful tool, and there are certain things that simply cannot be done without AI, such as correlating these anomalies that we detect to part defects. When we're looking to predict something like, will this part perform? Will this part pass quality inspection after the part has been printed, after support structures are removed? That's where we believe that AI will really make a difference, is the prediction and the estimation and relationship between certain things like anomalies, porosity, fatigue life. So that's what we're focused on at Phase3D, is using inspection technologies to measure the process with repeatable and calibrated data, then using AI to do things like performance prediction and correlation modeling.
Beautiful. Thank you, Niall. We have time for one more question here. And so from Caitlin, she's asking, since the units are quantitative, can the data be compared directly between different machines, models, regardless of the calibration? I'm also going to add to this question here. Andrew, can you also describe all the different machines that we have systems readily available for?
Yeah, and Caitlin, to answer your question, yes, it can. And it also allows you to do things like compare data from one machine to another. So if you're running production builds and within your entire facility, let's say you have 15 US M290s, you want to compare builds from one machine to another to see the actual performance. Because we do have calibrated and quantitative measurements, you can actually do that. In terms of what we actually have systems ready for, we work with a lot of machine manufacturers and we've installed on many different ones. EOS, for example, we have a system activator for the EOS as well as the Concept Laser M2. And we've also worked with DMG Mori as well as Renishaw. And of course, we can do custom solutions as well.
Beautiful. And I'll add to Andrew here. One of the key differentiators for us compared to any of our competitors is because we are not relying on the light source within each machine. You're able to compare one-to-one for height maps from, let's say, a EOS M290 to a SLM 280 with the same build size. You can also do the same as you scale up, looking from like an EOS M290 to a M400
400.
for
Yeah.
exactly. Especially
Yeah.
within this industry as we scale, this is a key feature to it. We are out of time here, so I want to thank everyone for their time and really appreciate it. We will be releasing this recording so you can share it with your colleagues. And thank you, everyone.
Thank you.
Sure.